Hello, welcome to section 3 of chapter 8. So this time we are testing the difference between means again. So that part's exactly the same. This time though, our two samples are dependent samples instead of independent. So just a reminder, dependent samples is when you're using the same people but taking two different measurements from them for the two samples. So this could be something like a before and after type of data set where you had a group of people and you measured their heart rate before they did a bunch of exercise. And then you measured the same people's heart rates afterwards or something like that. So for our first example, we have a shoe manufacturer that claims that athletes can increase their vertical jump heights using the manufacturer's training shoes. So the vertical jump heights of 8 randomly selected athletes are measured, and then after they use their shoes, they measure their vertical jump height again. So we're hoping that the vertical jump height should be higher the second time because, these shoes are supposed to be good for them or whatever. Is there enough evidence to support the manufacturer's claim? Assume the vertical jump heights are normally distributed. So here they've listed out, this was how tall they were jumping before using the shoes for each of these 8 people, and then after using the shoes. So again, we want to see that increase because your shoes are supposed to help you jump higher. So before we start, we want to check our conditions. It's the same 3 that we've been doing for a while now. So we want to make sure we have random samples, and in this problem, they did tell us the athletes were randomly selected. And then we also want to check for a normal distribution. So we either want the problem to say normally distributed, which our problem does, or we want our sample size n to be greater than 30. So here our sample size is 8 because we're only looking at 8 people, even though we have 2 sets of data for the same 8 people. So that's why it needed to say normally distributed. And in our previous problems, we wanted to make sure we had independent samples. Well, now we need dependent samples. So here we have dependent samples because we're using the same 8 people each time. Okay, so those are the 3 conditions that we want to check. So for these problems, because we're looking at the same 8 people, we actually want to look at the differences between each person. So rather than looking for the mean of the first set of data and the mean of the second set, and then looking for the standard deviation of the first set of data and the standard deviation of the second set, we're actually only going to find one mean and one standard deviation. So in order to do that, we want to find the difference between their before and after score. So that'll be our first step. So for each of the numbers that they have for each person, we want to subtract them because that's what a difference is. So normally we usually do before minus after, and that's pretty much what you're going to do every time. So if we subtract these 2 numbers, you're just going to write all the differences underneath, and those are the numbers that we're using to find our mean and standard deviation. Okay, so I've calculated the differences, and then we're going to calculate the mean and standard deviation of those differences. And I know we all are at home, so I don't know if you guys have graphing calculators or not. If you have a graphing calculator, hopefully you remember how to use it. I'm going to show you really quick on mine so that just to give you a little bit of a refresher. If you don't have a graphing calculator, it's okay. I'm going to send you a link of a website where it'll calculate these things for you, because otherwise doing it by hand would take forever. Okay, if you have a graphing calculator, so the first thing you want to do is to type in all your differences, just those numbers that we got from subtracting, into a list. So if you've forgotten how to get there, remember you want the stat button and then edit. So I've already typed in all my numbers into L1. So we have 8 numbers total, so you just want to make sure that you also, the last one, the blank one, will be like L19 because the blank one will be the 9th number. So that means the one before is number 8. So quit out of this so that we can calculate the mean and standard deviation. Quit is the button above mode, so second and then that button. And then to get to calculating a mean and standard deviation, it's the button above the stat, because remember, stat is our favorite button. So second stat, and then go over to math. So number 3, you'll see mean. Number 7, you'll see standard deviation. So let's say I'm trying to calculate the mean first. I want to find the mean of everything in my L1. So L1, we're going to type in the second and then the number 1 button. End your parentheses and hit enter. So our mean is going to be negative 1.75. And then we're also going to calculate the standard deviation of our differences. So that'll be second stat again. Go over to math, and we want number 7 to calculate our standard deviation of L1. So we got 2.121. We'll just go 3 decimal places for everything. Okay. So basically, when we deal with dependent samples, we're only dealing with this set of numbers. So we're going to get one mean, one standard deviation, and that's what you're using to calculate your test statistic and everything. Everything else, though, is pretty similar. The newest thing would be our hypotheses. Instead of mu1, mu2 in our hypotheses, it's actually going to be mu with a little like lowercase d next to it. It stands for the differences. So we're saying the mean of the differences, and then we're going to do like greater than, less than, all of that. So I'm going to look back at my original problem. The claim was that the athletes can increase their vertical jump heights using the manufacturer's training shoes. So if their jump heights are increasing, so whatever number they had before, the after number should be higher, is what they're claiming, because you're jumping higher. So if the second number is higher, when we subtracted this, a smaller number minus a bigger number should give you a negative number. So they're saying the mean of the differences should be less than 0, because any numbers less than 0 would be negative. And that's how I knew it was going to be less than. So that means my HO then would have to be greater than or equal to 0. Alpha, they told us, was 0.10. And then our test statistic is going to look like this. So this D with a line on top, that stands for the mean of your differences. So we got negative 1.75 for that. Mean of the differences, the mu D would be our number that we used here. It's usually going to be 0. And then on the bottom we have SD. That's your standard deviation of the differences that we found up here, divided by square root of n. N was your sample size, so we had 8 people in our sample. So that'll be our setup for the test statistic. When you do that in your calculator, you should get negative 2.333. Okay, then in our rejection region, so other thing that I wanted you to pay attention to, we are back to t-scores. T-scores meaning the t-distribution. So we're back to our green charts. So in order to use the green chart, we have to look at our degrees of freedom again. It's just n minus 1. So for us, our n was 8. Subtract 1 would be 7, would be our degrees of freedom. And because this is alpha of 0.10 and it's a one-sided test, because we are shaded to the left only, since our HA is less than, then when we look at our green chart, degrees of freedom of 7, this is a one-tailed test of 0.10. Going down, we see that the number is going to be 1.415. Okay, 1.415 is a positive number, but because we're on the left side, we're going to end up being negative. Remember, you have to change it to negative yourself. Our test statistic was negative 2.333. If 0 is in the middle, 2.333 would be like somewhere in that shaded region. So that would mean we would reject. I feel like we've gotten really good at our decisions. So at this point in time, you don't need to write out your full decision anymore. I think you've gotten it. Like, we're going to save ourselves some time. So I just need to know whether you're going to reject HO or fail to reject HO. And I'm very happy with that. Okay, So that's it for this type of problem. I'm just going to do one more example where it's two-tailed, just so you know, you get the hang of it. But if you got it from here, cool. So my second example is similar. So again, we are getting last year's data with this year's data for how people voted, or their performance rating. And N is 16 here because we got 16 different people. So we have randomly selected voters. So our random condition is met. We have dependent samples because these are the same people both times, and they told us it was normally distributed. Okay, so before we start, we want to calculate our differences and find the mean and the standard deviation of those differences. So I went ahead and subtracted everything. I did last year minus this year to get all my differences. Then I went ahead and did the mean in my calculator and got 3.3125, and the standard deviation was 9.680 if I rounded correctly. So once we have those pieces of information, then I can go ahead and do my hypotheses. For my HO and HA, in this problem, they were trying to see, so their claim was to determine whether the legislator's performance rating has changed from last year to this year. So whether it's changed or not would be like, is there a difference? Is there not a difference? So if it didn't change, then when you subtract the two, then we're saying that the difference would be 0, right? If it didn't change, then if it did change, then it's just not 0. So my hypothesis is that it's going to be either equal to 0 or not equal to 0, because they didn't specify whether it like increased or decreased. And then alpha was 0.01 here. For my test statistic, the formula looked like this. So filling everything in, my sample mean, or the mean of the differences, was a 3.3125. My mu d was 0. And then my standard deviation was 9.680 divided by the square root of n. Well, n was 16 in this problem. When I do that in the calculator, you should get 1.369. And then drawing out my rejection regions, my HA was does not equal, so that means it's a two-tailed test. So I got to shade both sides. And then degrees of freedom for this one is going to be 16 minus 1, which is 15. So looking at my chart, at the top, I have, this is a two-tailed test. Alpha was 0.01, so I'm looking at this column over here, and then go down all the way until I see degrees of freedom of 15. So that would end up being the 2.947. So 2.947 is the positive value. So that means on this side it would be negative 2.947. Our test statistic was 1.369. If 0 is in the middle, that means it's like somewhere here. So it didn't get shaded, so we would fail to reject HO. Okay, that's my decision. That's it for this section. We just got one more section to go after this.